Alrighty, so back again, another question. This one is going to be the kth smallest element in a sorted matrix, and we'll get into that shortly. Just give me one moment. Looks okay. Yep, looking good. Okay, so we'll go normal. Alright, kth smallest element in a sorted matrix. Let's see it. Let's see how this goes. Given an n by n matrix where each of the rows and columns are sorted in ascending order, return the kth smallest element in the matrix. Note that it is the kth smallest element in the sorted order, not the kth distinct element. Excuse me. So I have this matrix. K is 8, output is 13. Elements of the matrix are 1, 5, 9, 10, 11, 12, 13, 13, 15, and the eighth smallest number is 13. So a few things. I think there's a couple things to say about this question. I think I got it. I got the idea, and I got what to do, and all that. I think. So we have to be careful when we say O of n. I'm going to say O of m instead of O of n, where O of m is the number of elements in the matrix, because it's n by n they're using. So actually it's going to be n squared elements, so m is going to be n squared. A little confusing, but this is basically intro select kind of a question. That's what to get to the kth smallest element, you would use something like intro select. That's, I think, one of the best ways to do it. And interestingly enough, C++ has an nth element. It has actually a built-in implementation for in the algorithm library for the intro select. So that's awesome. That's really nice. So you don't have to try to figure that out for yourself, how to do that. Yeah, so you have this iterator. Basically, you take an iterator and you said let that. That's gonna be set to that element. So the deal is we want to. It's gonna go something like the following. We want to. We could dump this entire matrix into a single array and sort it, and then find the element that way. That's one approach. That would give you n log n time. It's not really the best way to do it. Or m log m time. Rows and columns are going to be sort of non-degreasing. Bold non-degreasing order. Awesome. What we want to do, so we can do n log n time. We can do another approach is to actually just literally dump the whole matrix into an array and to perform intro select on it, because you don't actually need to be sorted to find the element in using intro select. So that's linear time. And then finally we can do, I want to say we could probably do this in logarithmic time somehow, because this is already sorted. So can we do this in some kind of logarithmic time? That's the question, I think. Yeah, so each of the rows and columns are sorted in ascending order. So that's kind of neat. It's not really that great to be able to do it in O of m time. Like I said, yeah, you can just dump everything into a single array, and then that's that. Can we do it more efficiently or faster, something smarter, more clever? I think that's kind of like the crux of this problem is can you do it in a more clever way? There's alternatively square root of m or n O of n time, which is You can kind of like trace out the matrix to find the element. Sort of. Actually, it's really O of k time in that instance, I think. I still think you do this in logarithmically, somehow in logarithmic time. I don't know if you can though. I just think you can. I'm just guessing you can. I don't actually know how you can do it. I don't know. I don't know. Let's ponder that for some time. Let's go ahead and ponder that for some time. It's sorting in ascending and descending order. Or excuse me, it's sorted, the rows and the columns are sorted. That's pretty interesting. The problem you run into though is if you I guess you always have four options to pick from. At most 4 options. So yeah, I think you can do this in O of k time. But I think you can do better than that still, even still. Why though? How could you do it better? I don't know that you can. I don't think so. This reminds me a lot of the just finding a particular element in a sorted array or sorted matrix, which I'll show you there's a solution to that. I'm going to implement the same solution that's the O of k solution, but it's O of n plus m time, and there's like some debate on like what the optimal solution is and how to achieve it, but basically it has something to do with like using a binary search on the longer edge and a linear search on the shorter edge of the matrix, something like that. And that's kind of the optimal approach, which is an idea here. I guess you could do the same thing here. You would do a search or binary search on the row. And so if there's more rows and less columns, depending on which one's which, you would do. So suppose the rows are, there's more columns, the rows are longer. So we'd use binary search on the rows and linear search on the columns. And the binary search is going to be basically, you're going to move through the row up until a point where the element, the next element in the column in the next row, the element in the next row, basically you're going to find the first element of the next row. You're going to search for that in the first row. The first element in the next row, you're going to logarithmically search for that in the first row, right? Because it's sorted, so everything. So yeah, so the first element you find in that row, all of those elements come before the first element of the next row. If that makes sense, when you do that, perform that binary search. And because things are sorted, you know that sort of those are all the elements in the row, the second row that are larger than that element are also going to come after the elements that you're looking at right now. So you can kind of safely discard however many of those there are. And if there's still more values in k, then what you're going to want to do is, see, I don't know if you, from there, if you, to perform a binary search on the second row, to remove elements there, excuse me, and then I guess you would come back to the first row we go some amount in the second row. Just thinking, yeah, you go some amount in the second row, and then you go back to the first row and do another binary search again. That isn't necessarily faster. No, it's not actually. It could actually be less efficient. I'm thinking about it. So for this problem, it's arguable whether or not it's even better to use logarithmic searches. Huh. No kidding. Wow. Okay. Okay. Just thinking about like if you just have an array and you're looking at sorted columns and rows of a matrix, and you're just looking for a particular element, if it's in there or not. Yeah, and you do the logarithmic search from left to right, and then you would drop down one row, let's say, and then do another logarithmic search, and then drop another row, another logarithmic search. Excuse me. Why is that different from O of n plus m? Not just O of n plus. Why is that different from not O of n plus log m and not O of n times log m? I think it is O of n times log m. Yeah. I think it is. I think it is. Interesting. Anyway. This is going to be our O of k, which is O of n, or if k is large, solution. So let's try that. So we're going to say, basically start in the top left of the matrix, and then the neighbors of that element are going to be candidates for the next, right? So basically sort the neighbors, only four, at most it's going to be four, so sorting is fine. Sort the neighbors, get that next, move to the next position, depending on which of those is the correct next element, and then you get two more neighbors to pick from, depending on which direction you go. So now you have three to pick from, and you would update depending on which one you pick. So you remove the position you're at, remove the two neighbors associated there, and yeah, I think we'll use an unordered set to do that, to do this, to kind of maintain the neighbor set. I think that's simple enough. So we'll maintain a neighbor set, and then you just, we'll use a utility as well. We don't need algorithm anymore. So yeah, we'll do it this way. I like this approach. So basically maintain this neighbor set and manipulate this neighbor set and kind of traverse the matrix. So we'll have a starting point, int row, column for int I equals k, I is greater than 0, minus I. We'll do k number of times. So my neck is aching. Nice. Spent 15 minutes just thinking about the question. It's good. Oh no, it's not unordered. This is an ordered set. Not unordered. This is going to be kind of a tricky thing. Okay. A pair of int to tuple of ints. Yeah, a little tricky. I don't think we need to add tuple pair set. Okay. Yeah. Kind of an interesting data structure that we're going to be using, but I don't think we need to add any logic here to have this sort properly, but it's going to sort on the first key. That's the most significant key automatically. And that those are going to be, it's going to be the pair, it's going to be a pair of the value in the matrix and then the row and column index of that matrix. And so this is going to be the neighbors that we're going to work with. So yeah, it was kind of that was one of the things I was kind of thinking about. I was like, how are we going to implement this neighbors logic here? And I think we can use this data structure. I think it has a lot of stuff in it that kind of sort of do a lot of the things we want automatically. So initially our neighbors are going to be, we're going to say it's matrix of row plus 1 column and column plus 1. So move to the right, move down and move to the right. Right, moving to the right is adding 1 to the row, and moving down is adding 1 to the column. And then the pair that's the value, and then it's going to be make tuple of row plus 1 column. Yeah. Something like this. That looks a little confusing, I think, but I think it's okay. Might look a little confusing at first. And we say, so we're going to take from the neighbors. Also the matrix is empty. Okay, the matrix is not empty, so we can start off with first things first. We can say excuse me. We can just start off with k minus 1. So we initialize the neighbor set with these two and set k minus 1. That's if we actually don't even want to do that. I'll explain why in a minute. Basically, if, whoops, kind of want to do something like this. Sorry, this is a little confusing what's going on here. So I'm trying to avoid like the out of bounds errors, I guess, exceptions. There's a few things I'm trying to avoid. What do you think? First things first, the first element in the set, we don't need to even add that to our neighbors. Like our neighbor set could be initialized as described here. The problem is, shoot, there's like a bunch of things. I'm sorry, I'm kind of like stumbling over myself here. There's like a bunch of things at once I'm thinking about. Okay. If k is 1, k is non-zero too, right? Yeah, okay. If k is 1, we just want to pass right through and return this. That's what I'm trying to say. So if, right, k is 1, so we subtract 1. Okay. If k is 2, then we want to call this loop, and we don't even want to put neighbors in there if k is 1. It doesn't really matter if we do that or not, though. And the deal with the neighbors is we kind of want yeah, okay, I'm sorry. It's a little confusing. This is a little confusing. It's very confusing, actually. I don't know if I'm doing this the right way. So what we want to do is take the minimum element. So we have a neighbor set that we're considering at each step, and we'll take the minimum element of that neighbor set, and that'll be the next sort of value leading up to k, right? However, when we take that, we need to update our neighbor set appropriately. So we can add values to the neighbor set in the direction that we've now extended into. However, we also want to remove the other neighbors that were adjacent, right? If that makes sense. And that's why we want to include the value as well as this tuple that tells you where it is. I think we're fine. I think we're okay. I think we can manipulate that. I think it's fine. But that's what we do each time. So so select from the neighbor set a new value, select a new candidate. Yeah, so we do want something like this. Our inbounds check here matters. R is less than the number of rows, and C is less than the number of columns, right? So row, column, inbounds, check. Okay. And we say if inbounds of row plus 1 column, then we want to do this. And the same thing here. Row and column. Obviously, you can kind of make like a subroutine out of this too, so that way it's sort of consistent. The row, the row plus 1 is consistent and column is consistent across, and the same thing rows across consistent across and columns consistent across. I think we don't use this enough where it's fine if we kind of just leave it as is. We do want to do an inbounds check. So now, okay, great. Let's do that. So select a new candidate from the neighbor set. We're going to say auto candidate is going to be neighbors dot begin. Right now, the way that this is sorted, we don't need to make a reference either. Wait, excuse me. The way this is set up, this will automatically pick up the smallest value in the set, and these other pieces will just kind of come with it. So then, once you've selected that candidate, remove neighbors, current candidate, current neighbors from the set. We'll do that first. So we would say we want to get the row and column from the candidate. So it's going to be candidate dot second is what's going to give you, oh yeah, this is an iterator. That's going to get you the tuple, and the row is actually, it's going to be get the first element, the 0th element of this, and same thing. C is going to be get 1 from this guy. How long have we been doing this? 27 minutes, so it's kind of a while. I don't think this should be that difficult, but I guess we're kind of struggling our way through this. So at this row column, now we say if in bounds of r plus 1 c, then we're going to neighbors dot erase. It's going to be matrix of r plus 1 c. It's going to be, we're going to have a key. So we're going to auto key equals this guy. Generate this key. Create a pair of r plus 1 c. Make tuple of r plus 1 c. Create this key, and then delete. Erase this key. Same thing. Instead of r plus 1, it's c plus 1. Okay. So the current neighbors that are in the set, we're going to remove both of them. R plus 1 C and R C plus 1. Okay, that looks right. And then add new neighbors of the candidate to the neighbor set. So actually I'm wrong here. Move the candidate current neighbor. So it's actually going to be previous values current. Now, yeah, see that's a question. It's not the previous values neighbor set that you're going to remove. It's, so I got this wrong. Have this neighbor set, and we say, okay, we're going to add this now. we're going to remove the value that we're about to add. We're going to remove that from the set of neighbors and then add a couple more neighbors. Just thinking about how this could look. I could probably draw it, but maybe not. Well, the neighbors might already be there. These sets are unique with respect to the elements in them, so it really shouldn't be an issue. I just think. I don't know if it really matters if we remove. I don't think we need to remove anything. Now I'm thinking about it. I'm not sure if that really matters. In that case, though, it does seem. Huh. Just thinking some more here. This seems like it'd be better implemented with a breadth first search, by the way. Where the queue is somewhat sorted. I think that's kind of what we're going to end up implementing here. Something of a breadth first search. I think it doesn't matter if you. I think you just remove the. Yeah, I think I got this wrong. I think I got this wrong. I think you just remove the candidate from the neighbor set and just add the other ones in, leave them in. I don't think it matters. I think it's actually correct to leave them in there. So remove the candidate from the neighbor set. That's RC. And so these are, and of course you don't have to do the inbounds check because you know it's this is just candidate first. Really, you could just erase the candidate altogether. I don't think you even need to do any of that. I don't think it matters. I think this is almost verbatim, same code as we have up here. They're really similar. I don't know, man. I think this is not going to be as I thought either. I don't think it's actually going to be, constant time at each step, sort of. Well, it is constant time at each step, but the insertion is going to be logarithmic time. So you'll have log k, I think, is going to be the total runtime. Something like that. Yeah, something like this. What does this look like? What does this do? Yeah, okay. Something like this. Runtime error. Wow, worked. Okay. Should we just run this? Just go for it? Yeah, just go for it. Hey, we got there. Sweet. So we're slower than a lot of other solutions. I don't know. This one was kind of a tricky solution, I guess tricky problem. I don't think this is good what I did. Now that I'm looking at it, thinking about it. I thought it would be efficient to do it this way, but one, it took forever to code. I mean, we're looking at almost 40 minutes now. And two, this would have been so much easier to just dump the matrix into a set of numbers and then perform intro select on it. That's actually probably more efficient, and it's probably about as memory consuming as this is, right? Because in some cases the memory for this could be expensive. So I'm not sure if there's really a benefit to doing all this effort. It was interesting, but let's try the other approach, which is just dump into an array. Perform intro select. And I think this also has 1, 2, 3. Oh yeah. Excuse me. Nice. What is going on here? What is going on? It is right. Interesting. So is that right? What? Oh, because no. What? Is that what's wrong? Oh, yeah. Okay. Yeah. So this is like a super simple way to do it as well. I think this is probably more efficient in a lot of cases too. Oh, ouch! Really? No kidding. Take that back. Wait a minute. Whoa. Whoa. Wrong answer. Output 1, expected 2. This is the third element from, should be 1123. Third element from 1123, huh? Should be one, yeah, should be one, should be 2. What did we get? 1? Huh. Now, what? What? Maybe I did this wrong. Yeah, I think I did it wrong. Because it's not, it's this k, the kth element, it's an index k minus 1. So really yeah, I think it's, okay, got there. Yeah, it's a lot faster. And it's less memory too, which is weird. Yeah, that's my mistake. I kind of I misconstrued or confused, misconstrued and or confused basically the index for k. This is like a direct index, this value, whereas this is the I don't know what you call it, the sort of the nominal position. It's not zero index. This isn't specifying by zero index, whereas this is specified in zero index. So it's going to be k minus 1. And that's also why I got the wrong answers, because I had a mismatch in these indices. But yeah, this is a lot simpler to code, right? A lot simpler to code, a lot simpler to understand. Like you could do this in a few minutes this way. And as you saw, it kind of uses less memory anyway, because this approach is like kind of a BFS type of thing. But the problem with this is that you kind of need to keep track of your neighbor set anyway. And that could take a lot of memory, and you're also trying to find the optimal, I guess you could implement the neighbor set as like a priority queue to avoid like basically keeping that neighbor set sorted instead of using a set. So you introduce that extra logarithmic term, but even with a heap, I think you still have logarithmic terms anyway, so like keeping all that sorted is more expensive in terms of time. So it actually takes, and not to mention you have all this extra machinery going on too of like these different concepts and data structures and all that you're using. So I think it's better to just keep it simple and dump it all into an array and then intro select the array and just don't worry about it. Yeah, get your nice 80, better than 82% and call it a day. Get 95% of the solutions. It's kind of funny. That is kind of comical. It's like this is still linear time, and that's actually this other one is not linear time, or rather, well, yeah, just say it's. We'll just say this. I kind of prefer this. Yeah, this is fast and relatively efficient on memory and space complexity, or yeah, space and time complexity is relatively efficient. So and it's super quick to code, as you see. It's like really simple to understand and code. So yeah, let me. I'll keep the rest of this as it is. You know, I'll keep it how it is. So I have my submission, so I can always kind of come back to the submission. But yeah, so thank you for watching that one. That could have been a lot faster. That really was like a lot of time for something that was like could be done in like a few minutes. Kind of interesting, but I was trying to figure out a way to do this. I was trying to figure out a way to do this that didn't involve using so much memory, and I couldn't really come up with a way that wouldn't use a lot of memory. Like I was trying to use sort of the neighbor related thing, but yeah, as kind of stated before, you kind of need to maintain like a lot of neighbors to do this correctly. Yeah, so it gets awkward. It's actually kind of a lot of memory to consider using. So all right, so let me go. Thank you for watching this one as well, and I'm gonna go ahead and what was I saying? What was I doing? I'm gonna go ahead and end this live stream. Say thank you. Take a moment or two and probably do another problem. Just kind of keep going, I think. But yeah,